Hello and welcome to Vodcast 13.3. In this podcast, I will overview highs and lows. I'd like to start off by overviewing low pressure centers, or Ls. In the weather world, you can kind of think of the red Ls as being the villains that bring about bad weather. Now, by definition, a cyclone is a center of low pressure. Now, don't confuse the term cyclone with tornado. While it's true that tornadoes are cyclones, not all cyclones are tornadoes. In fact, if you take a look at the mascot for Iowa State, it's not technically incorrect, although it is kind of misleading. So our red L's that we see on maps don't always indicate tornadoes, but they do always indicate cyclones, which are centers of low pressure. So if you take a look at the map shown on the right, where you see the red L is the lowest pressure region on the map. As described in a previous vodcast, air wants to flow from high pressure regions to low pressure regions, so air wants to flow towards the red L. If you start your voyage out in the Rocky Mountains and start moving towards the red L, you would notice that the pressure gradually drops as you approach the cyclone. Now, two very important things I have to overview are shown in red. In the northern hemisphere, the winds will be directed inward, and at the surface, we will see convergence. Another important thing to note about cyclones is that the winds will work counterclockwise around the low pressure center. Now keep in mind, if the Coriolis effect did not exist, the winds would cross all of the isobars at right angles and work their way straight to the center of low pressure. But the Coriolis effect does exist, so the winds do not cross the isobars at right angles. Let's focus on this red arrow indicated right here. In the absence of the Coriolis effect, this wind would actually want to take the path shown here, because this would be the most efficient path in moving from an area of high pressure to an area of low pressure. But the red arrow indicated is actually deflected to the right of that path. And if you were to focus in on any of the red arrows shown on this map, all of them will be deflected to the right of the path that would take them straight down the pressure gradient, perpendicular to all the isobars. So in summary, a cyclone is a center of low pressure, and in the northern hemisphere, we will see surface convergence of winds, and the winds will work counterclockwise around the low pressure center. On this slide, I like to show two cyclonic storms, one occurring in the northern hemisphere and one occurring in the southern hemisphere. But if we start off by focusing on image A, we see a satellite image that shows a low pressure center in the Gulf of Alaska, which is in the northern hemisphere. As we would expect, the winds are spiraling inward towards the center of low pressure. I tend to think that the clouds associated with these cyclonic storms look like Cinnabons. But the point is, this image shows us very good visual evidence that surface convergence is occurring. Also notice that all of the red arrows are oriented in a counterclockwise manner. In the northern hemisphere, the winds will work counterclockwise around cyclones. But now let's shift our attention to a strong cyclonic storm in the southern hemisphere. In the southern hemisphere, we still have converging winds. However, the Coriolis effect acts in the opposite direction in the southern hemisphere. Instead of the winds being deflected to the right, they're deflected to the left. So in the southern hemisphere, we would see the winds working in the clockwise direction around the low pressure center. Now let's shift our attention to high pressure centers, or H's. We call high pressure centers anticyclones. So hopefully that's pretty easy to remember. Low pressure centers are cyclones, high pressure centers anticyclones. Now the winds associated with an anticyclone in the northern hemisphere will be outward from the high pressure center. Another very important thing to note about anticyclones is that the winds will move in the clockwise directions as they work their way out away from the high pressure center. So just as before, I'd like to focus in on one of the red arrows just to kind of reinforce the Coriolis effect concept for you. In the absence of the Coriolis effect, air will want to flow from a region of high pressure to a region of low pressure in a straight line. So air coming out of the high pressure center here would want to travel this path shown on the screen. However, due to the Coriolis effect, the winds will be deflected to the right in the northern hemisphere. So that's why you see this red arrow veering off to the right of the line I've indicated on the screen. Earlier in this vodcast, I mentioned that cyclones are often thought of as the evil villains in the weather world. Anticyclones can kind of be thought of as the heroes, if you're a fan of fair weather, sunny weather, going to the beach, and things of that nature. One other thing to note about anticyclones is they're associated with subsiding air. With cyclones, we had converging winds, and convergence is one of the mechanisms that helps force air aloft. But anticyclones are quite the opposite. They're associated with air actually subsiding. And on the next slide, I'm going to overview just what I mean by that. This final picture you see on the screen is very important, because it may have occurred to you that if we focus in on the cyclone shown on this map, the low pressure center, all of the winds are blowing into the low pressure center. And what that basically means is we're putting a lot of air into a small little region. Well, there's a problem, because if there's a lot of air in that region, that center's not going to have low pressure for very long. The more air we try to squeeze into that region, the higher the pressure will get. So the question is, how do we maintain a low pressure center? Because low pressure and high pressure centers can be maintained and last quite a long time. Well, this picture shows exactly what happens to help us maintain that low pressure center and maintain that high pressure center over a long period of time. If we focus in on the low pressure center, we see converging winds, and they're working in the counterclockwise direction as they spiral in towards the low pressure center. But as those winds converge, you can almost imagine the air piling up as we near the center of the cyclone. And as that air piles up, it gets forced aloft. And when that air is forced to move upward, we can see adiabatic cooling, cloud formation, and storm development. But if we focus in on what's occurring high in the atmosphere above the cyclone, we actually see divergence aloft. And it's very important that there's divergence aloft over the top of a cyclone, because as more air moves its way upward due to convergence, there has to be somewhere for that air to go so that we can maintain that low pressure center at the surface. Now, what's really interesting about the cyclone is that the divergence aloft and the convergence at the surface are pretty well balanced most of the time. But if divergence aloft starts to occur at a more rapid rate than convergence at the surface, you might start to see some really strong surface winds and the formation of some very powerful thunderstorms. That converging air at the surface is going to be sucked upward at a higher rate to fill the void left by the air leaving aloft. Now at this point, I'd like to shift your attention to the anticyclone, which you see as the blue H shown on the map. At the surface, we see diverging winds, and we see that the winds are moving in the clockwise direction as they move away from our high pressure center. But to maintain that high pressure center, knowing that air is moving outward and away from the high pressure center, we have to imagine air is being fed into the high pressure center from convergence aloft. I hope this makes sense, but in order for winds to work their way outward away from a high pressure center, the anticyclone has to be fed air that's capable of diverging outward and away from it. So it's really important to note, when taking in this slide collectively, that cyclones and anticyclones kind of rely on one another. Because in order for both to be maintained, there's a very important air circulation mechanism that benefits both of them. For a low pressure center to be maintained or strengthened, the surface convergence must be balanced by divergence aloft. Simply put, if we are not seeing divergence aloft, that low pressure center cannot be maintained. And by the same token, for a high pressure center to be maintained or strengthened, surface divergence must be balanced by convergence aloft. Without convergence aloft, the anticyclone cannot be maintained. Okay, that's the conclusion of this video podcast. In our next vodcast, we will consider general worldwide circulation in our atmosphere.